Today we're going to talk about topic 3.1, thermal concepts. And we'll start with addressing the idea of temperature. At the macroscopic level, when we talk about temperature, we're talking about how hot or how cold something is. And you can think about how you relate this in your everyday life. You're talking about the temperature outside or the temperature of something that you eat or drink. You're talking about how hot, how cold it is. And it's really in relation to you, so it's to some extent it's relative. But the most important component of the macroscopic temperature idea is that it determines what direction energy is going to flow when two objects are in contact with each other. Energy has a natural tendency to flow from high energy to low energy. And so when we're talking about thermal energy, it's always going to flow from the higher temperature object or higher temperature substance to the lower temperature substance. And that energy is going to flow until the two objects are what we call in thermal equilibrium. And thermal equilibrium is when the two objects are at the same temperature. At that point, when thermal equilibrium has been reached, the net flow of energy between the two is zero. And so to understand the why, it's important to understand what exactly temperature is. And when we're measuring temperature, and we know there are a variety of scales, we'll talk about those in a few minutes, we're really measuring the average kinetic energy of a substance. And we use things like mercury thermometers or alcohol thermometers, and we're using a property of those substances called thermal expansion. And so when a liquid gets warm, it starts to expand because those molecules start to spread out. And so we use the thermal expansion of the liquid in the thermometer to measure different temperatures. And we put the graduations on the thermometer in alignment with the scale that we're working with. And that liquid in the thermometer, essentially what's happening is when you put the thermometer into a substance that you're measuring the temperature, it's getting into thermal equilibrium with the substance that it's measuring the temperature of. And so if you put it into a hot substance, energy from that hot substance flows into the thermometer. The liquid in the thermometer expands, and so you see the temperature rise. If you put it into something cold, energy is actually flowing from the liquid in the thermometer into the substance, and so the liquid in the thermometer is contracting or condensing, and so that's why you see it move down the tube. Our scales that we use, and the scales that we use in this class, are going to be Celsius and Kelvin. We're not going to worry about the Fahrenheit scale. We're going to use our two metric system scales. The Celsius scale was developed in 1742 by Andreas Celsius, and it was provided a little bit cleaner scale than the Fahrenheit scale. The Fahrenheit scale, the divisions weren't really even. They were weird numbers, -32 for freezing, 212 for boiling. And so Celsius essentially based his entire scale around the boiling and freezing points of water. And he said the freezing point we'll call 0, the boiling point we're going to call 100 degrees, and then we're going to break up all the degrees in between evenly between 0 and 100. And then about 100 years later, Lord William Kelvin came along and developed this Kelvin scale, and it's often called the absolute scale because when he developed the scale, essentially what he did is he took the Celsius scale, and so he used the same degree values that the Celsius scale used, but he set it so that the 0 degree mark on the Kelvin scale was absolute 0. It was the coldest that anything could get. Nothing can get below 0 Kelvin. It's the absolute 0 temperature. And so on the Kelvin scale, each degree, so if the temperature of a substance goes up by 1 degree Kelvin, it will have also gone up by 1 degree Celsius. So the value of each individual degree is the same, but the scale is offset, and it's offset by 273 degrees. And so 0 on the Kelvin scale is -273 degrees Celsius. Now at the microscopic level, when we're talking about temperature, what we're really talking about is the average kinetic energy per molecule that's associated with the substance. And kinetic energy is the energy of motion. And so if something has a higher temperature, it has a higher average kinetic energy per molecule, and so those molecules are moving around faster. As we decrease the temperature, we're taking energy away from those molecules and they're slowing down. Realize that when we say average kinetic energy, there's a range, and so there are going to be molecules that have a lot more energy than the average, and there's going to be molecules that have much less energy than the average. But most of them fall within a specific range of that average. And this average kinetic energy is directly proportional to the absolute temperature of the substance in Kelvin. And so what this means is that, again, it's kind of that definition of absolute zero. As we decrease the temperature, we're decreasing the average kinetic energy. Once we were to theoretically get to absolute zero, the kinetic energy of the substances would be zero. So if we now look at our ideas of thermal equilibrium from this perspective, when two objects are in thermal equilibrium, what that means is that the average kinetic energy of the two substances is going to be exactly the same. Understand, though, that doesn't mean the total energy is the same. If you have a bathtub full of water and you have a cup of water and they're both at 50 degrees Celsius, they both have the same average kinetic energy per molecule, but because the bathtub has much, much more water, the total energy associated with the bathtub of water is much larger than the total energy associated with the cup of water. Average kinetic energy there is the same, but the total energy is much different. There are also two additional terms that we need to be familiar with when we're talking about thermal energy. The first is the internal energy. And this is the total energy that's associated with the motion of the particles. And it comprises both the kinetic energy that we're measuring when we measure temperature and the potential energy of the molecules that they have based on their position. And so we'll talk about this a little bit more when we talk about phase change, but particles have some specific potential energy based on their position within the fields of the molecules around them, and that's our potential energy. There's also an energy associated with the motion, that's our kinetic energy. The internal energy takes into account both of these. And that kinetic energy, there are actually two types of kinetic energy that we have there. There's the translational, which just means the linear motion, the motion of the particles through space. But if you remember your chemistry a little bit, those molecules aren't, they're also rotating. They're not just flying through space, they're also spinning around, they're rotating around in response to what's going on around them. And so there's rotational motion, and there's also translational motion. So there's two types of kinetic energy that we can have associated with the molecules. And then, as we mentioned, that potential energy arises because of the intermolecular forces that the molecules are experiencing in that field. And so if we have energy flowing into a substance, it's increasing the internal energy. If energy is flowing out of the substance, the internal energy is decreasing. And then our third term is heat, and heat is that actual energy that's flowing. And so when we talk about the flow of thermal energy, we're actually talking about heat. And so it's important to keep these three terms separate and understand that they have three different meanings. When we're talking about internal energy, heat, and then we'll eventually talk about work, all three of them have separate, distinct meanings, but they're all measures of energy, and so they're all measured in joules. Now, one additional idea that we're going to have to be familiar with when we're talking about temperature and thermal energy and internal energy is the idea of moles. And again, hopefully you remember this from chemistry, but 1 mole is the amount of substance that contains the same number of elementary particles that there are in 12 grams of carbon-12. That's how it's defined. Experimentally, it's been shown that that's 6.02 times 10 to the 23rd particles. And that number, of course, is Avogadro's number. We can have an Avogadro's number of anything. We can have an Avogadro's number of particles, of molecules, of atoms. So we can have 1 mole of really anything. We can have a mole of pistachios. We can have a mole of marshmallows. It doesn't matter When we're talking about a mole, we're simply talking about 6.02 times 10 to the 23rd of something. And when we're looking at internal energy, we're talking about the energy that's associated with those particles, and so the number of particles that we have is going to be very important. And so to find the number of moles of anything, whether again we're talking about atoms or marshmallows, we simply divide the number of that thing that we have by Avogadro's number. So if we have 6.02 times 10 to the 23rd atoms, we have 1 mole of that atom. And so that goes for anything. Again, it's simply a little bit of dimensional analysis. And again, just to make sure that we're clear on notation, our capital N is the number of things that we have. And so again, I guess we'll just stick with molecules here. If we have 1,000 molecules, that's N. N subscript capital A is Avogadro's number, and then our lowercase n here, lowercase n is going to symbolize moles. And so when we see that in equations, that lowercase n, that's what it means. And then associated with that, we have our molar mass, and that's just the mass of 1 mole of a substance. And our units there are going to be grams per mole. And the reason that this becomes important is that when we're talking about that energy being distributed into a substance, different substances have different molar masses. And so when you have, for instance, a kilogram of lead, you have a different number of molecules than if you have a kilogram of something like gold. And so that energy is going to be distributed differently because there are a different number of molecules in each substance, even though the mass of that substance may be the same.